Okay, team. I know 12 million of people were in here. Now, where those 12 million people came from out of the few billion of us that are out here, I don't know. So, sit down. He's got important words to say, and we're going to listen to him.
Here, we look at the math behind an animation like this one, what's known as a complex Fourier series. Each little vector is rotating at some constant integer frequency, and when you add them together, tip to tail, the final tip draws out some shape over time. By tweaking the initial size and angle of each vector, we can make it draw pretty much anything that we want. And here, you'll see how. Before diving into it all, I want you to take a moment to just linger on how striking this is. This particular animation has 300 rotating arrows in total. Go full screen.
I don't think
this
is what he was doing at the time.
Working.
Yeah, no, this is... We are here.
Think about this. The action of each individual arrow is perhaps the simplest thing you could imagine, rotation at a steady rate. And yet the collection of all added together is anything but simple, and the mind-boggling complexity is put into an even sharper focus the farther we zoom in, revealing the contributions of the littlest, quickest, and downright frenetic arrows. When you consider the chaotic frenzy that you're looking at, and the clockwork rigidity underlying all the motions, it's bizarre how the swarm acts with a kind of coordination to trace out some very specific shape. And unlike much of the emergent complexity you find elsewhere in nature, this is something that we have the math to describe and to control completely. Just by tuning the starting conditions, nothing more, we can make this swarm conspire in all the right ways to draw anything that you
it
want,
only had this.
provided
You had
that
put
you
the
have
circle in
enough
it
little
and the
arrows.
wave function.
What's even
Okay.
crazier is
It's
that
like,
the
well, that's
ultimate
what did it.
formula for all of
No,
this is incredibly short.
not really. I lined all those ones out first, and then this one, and the
Now
little
often,
one in here.
Fourier series are described in terms of something that looks a little different, functions of real numbers being broken down as a sum of sine waves. That turns out to be a special case of this more general rotating vector phenomenon that we'll build up to, but it's where Fourier himself started.
You want to be here because that's here. If you're here, that's not good because then this is not what it's supposed to be because of this. And if you're here, it's real bad because then it's this.
I would like to teach you about Fourier series in a way that doesn't depend on you coming from those chapters, but if you have at least a high-level idea for the problem from physics, which originally motivated this piece of math,
it's
it gives some indication
in there.
for just
You
how
wouldn't notice it's one
unexpectedly
of them, but
far-reaching
it
Fourier
is.
series are. All you need to know is that we had a certain equation which
Well, I
tells
got
us
a
how
derivative
the
around here
temperature
somewhere. There it
distribution
is.
on a
Found
rod
it.
would evolve over time. And incidentally, it also describes
So,
many other phenomena unrelated to heat.
You don't
And
know
while
where
it's
you
hard
are
to
on this
directly
line,
use
really.
this
It's an
equation
apple.
to figure
No,
out what will happen
it's me
to an
throwing that
arbitrary
apple. No,
heat
it's points on a
distribution.
piece of
There's
paper.
a simple
Yes,
solution if the
kind
initial
of.
function
A
just
little bit.
happens to look like a cosine wave, with the frequency tuned so that it's flat at each endpoint. Specifically, as you
Camp 1,
graph
Camp
what
2,
happens
Camp
over
Lejeune.
time, these waves simply get scaled down exponentially, with higher frequency waves having a faster exponential decay. The heat equation happens to be what's
I
known
do
in the
not have
business as a
that you
linear
will find
equation,
plenty of heat in this
meaning
equation.
if you know two
I don't
solutions
exactly
and you add
have
them
the
up,
heat equation, but
that sum is a new solution. You
you
can
could
even scale
use
them each by
the
some
triple body
constant,
problem
which gives you some
iron
dials to
here.
turn to
That'll do
construct a
fine.
custom function solving
Certainly
the equation.
use the black body radiation
This is a
problem. There's
fairly
heat in there.
straightforward property
I'm
that
sure
you can verify for yourself,
it changes
but it's
things.
incredibly important. It means that we can take our infinite family of solutions, these
Feel like real
exponentially
close.
decaying cosine
There's
waves,
actually math in
scale
there.
a few of them by some custom constants of our choosing, and
The
combine
little
them
numbers and
to get a
P's and
solution
1s
for a
and
new,
MDs and
tailor-made
motion,
initial
mass
condition,
directions
which is
and
some combination of
we're
cosine
going
waves.
this way.
One important thing I'd like you to notice is that when you combine these waves, because the higher frequency ones decay faster, the sum that you construct will tend to smooth out over time.
They work
as
in
all the
place.
high
This
frequency
is
terms
the only.
quickly
I
go
need
to
a
zero,
slope.
leaving
This
only the
because
low
this is the
frequency
slope I
terms
have.
dominating.
This is I know.
So in a
This
funny
is
way,
known
all of the
here. We're
complexity
not
in
guessing
the
on this
evolution of
bite.
this heat distribution, which the heat equation implies, is captured by this difference in the decay rates for the different pure frequency components. It's at this point that Fourier gains immortality. I think most normal people at this stage would say, well, I can solve the heat equation when the initial distribution just happens to look like a wave, or a sum of waves.
Again, I
But
just
what a
thought it
shame
was
it is
fun
that
to.
most
Alright,
real-world
so I'm
distributions
putting
don't
a
at all
hot
look
mess.
like
Every single
for
axiom on
example,
there I could
let's say
think
you
of.
brought
Like I
together
think
two
I got them
rods,
all.
which
Like
were
this
each
one
at
I'm
some
getting
uniform
fancy with
temperature, and you wanted
parts
to know
and
what happens
quadrants and just making
immediately
it
after they
mad.
come into
But
contact.
here it's perfect. Now
To
it's
make the
just
number
one plane.
simple, let's say the
Hopefully the front
temperature of the left
plane
rod
from
is
the
1
top,
degree,
and
and the
then
right
I went
rod is
apparently
negative
down the
1 degree,
axiom this way,
and
but
that
you
the
probably
total
could have
length
come
L
down
of
this
the
way.
combined
But
two rods
in the way that
is
that's
1.
this, but I'm
What this
changing the
means
way
is our initial temperature
the plane
distribution is a
behaves.
step function,
So
which is so obviously different from a sine wave, or the sum of sine waves,
and they are
don't
very
you think?
different.
I mean, it's almost entirely flat, not wavy.
So you get playing
And for
around
God's
with this
sake, it's even
telescope, and that's the kind of
discontinuous.
thing I'm talking about.
And yet Fourier thought to ask a question which seems absurd. How do you express this as a sum of sine waves? Even more boldly, how do you express any initial distribution as a sum of sine waves?
They're
And it's
looking
more constrained than just
when
that.
they're doing this,
You
they're
have to
trying to
restrict yourself to adding
overclock a
waves
Game
which
Boy.
satisfy
That's
a
what they're
certain
doing.
boundary condition.
That's what they're doing
And as
right
we saw
here.
last video,
That's what we'll be
that
doing
means working
forever.
with these cosine
That's
functions,
why.
whose frequencies are all some whole number multiple of a given base frequency. And by the way, if you were working with some different boundary condition, say that the
No,
endpoints
this is
have to stay
overclocking
fixed,
a Game Boy.
you'd have a
What do you
different
mean?
set of waves at your disposal to piece together. In this case, simply replacing that cosine expression with a sine.
It's also twistor theory.
It's strange how often progress in math looks more like asking a new question rather than
So
simply
this
answering
rate's
old
got
ones.
butt.
Fourier really does have a
Drop
kind of
my Z.
immortality now, with his name essentially synonymous with the idea of breaking down functions and patterns as combinations of simple oscillations. It's really hard to overstate just how important and far-reaching
This
that
is
idea turned
Gannon.
out to be, well beyond anything that Fourier
Many
himself
like it,
could have
but it is
imagined.
his.
And yet, the origin of all this is a piece of physics which, at first glance, has nothing to do with frequencies and oscillations.
I know.
If nothing else, this should give you a hint
So
about the
sharp
general
about stuff.
applicability of Fourier's
That's
series.
teaching. Not even
Now
funny
hang on,
anymore.
I hear some of you saying.
Kinda funny.
None of these sums of sine waves that you're showing are actually the step function. They're all just approximations. And it's
Derivative.
true.
I
Any
mean, it's
finite
clocked
sum
in.
of
Got
sine
it.
waves
Check.
will never be
Well,
perfectly
then what'd you
flat,
do?
except for a
I
constant
started
function,
moving stuff around
nor
and
will
doing
it be
it. Really? You
discontinuous.
can do that? Yep.
But
sure
Fourier
can.
thought more broadly, considering infinite sums.
And
In
did
the
it
case of
and
our
did
step
math?
function,
You could do
it
the
turns out
derivative
to be
and do
equal
the derivative
to
of the
this
paper
infinite sum,
copy?
where the
Nice.
coefficients are
You're
1,
amazing.
negative 1/3, plus 1/5,
Do it in FZs for me.
minus
would you?
1/7,
Well, the force is
and so
no,
on for all the odd
no,
frequencies.
it's money.
And
You're
all
gonna
of it
need
is
money, and it's
rescaled
this
by 4
much.
divided by pi. I'll explain where those numbers come from in a moment. Before that, it's worth being clear about what we mean by a phrase like infinite sum,
That's what it
which
looks
runs
like.
the risk of being a little bit vague. Consider the simpler context of numbers, where you
Moving
could say,
along.
for example,
I mean, here's another
that
one.
this infinite
Got it
sum
on
of
the wall.
fractions equals pi divided by 4. As you keep adding the terms one by one, at all times what you have is rational. It never actually equals the irrational pi divided by 4. But the sequence of partial sums approaches pi over 4, which is to say, the numbers you see, while never equaling pi over 4, get arbitrarily
You would think
close to
that,
that
right?
value,
You would
and they
think, well,
stay
that's
arbitrarily
stupid.
close to
Why
that
would they
value.
do something like
That's
that?
all a mouthful to say, so instead we abbreviate and just say
Because of
the
this.
infinite sum
Now, they
equals
might have
pi
played
over
that
4.
for. I might have broke the rules.
With
Doing
functions,
things.
you're doing
This
the
might
same
be
thing,
this one.
but with many different
Or-
values in parallel.
Wait a minute. This one.
Consider a specific input, and the value of all of these scaled cosine functions for that input. If that input is less than 0.5,
Well,
as you
wouldn't
add more and more terms, the sum will approach 1. If that input is greater than 0.5, as you add more and more terms, it would approach negative 1. And at the input 0.5 itself, all of the cosines are 0, so the limit of the partial sums is also 0. And that means that, somewhat awkwardly, for this infinite sum to be strictly true, we do have to prescribe the value of this step function at
Not
the
exactly
point
sure.
of discontinuity
No,
to
it
be
has something
0,
to do
sort of
with
halfway along the jump.
the 4x4
Analogous
perfect
to an
square,
infinite sum
3x3
of rational
perfect
numbers
square,
being
because really
irrational,
you will
the
want to cut
infinite
this
sum
down.
of
How
wavy
would the photon?
continuous
I don't even care
functions
about it
can
anymore. We don't need the
equal, honest to
observation.
goodness, equal
And really
the
you don't.
discontinuous flat function.
The observation
Getting
comes.
limits into the game allows for
You need
qualitative
what's
changes,
up.
which finite sums
You
alone
need what's
never
up.
could.
You need to know
There
what
are
thing that
multiple
sounds
technical
like.
nuances
3B
that
gets
I'm
it.
sweeping
Yep.
under the rug
Okay.
here. Does the
And
fact
how
that we're
long it
forced into a
takes.
certain value for the step function
Top.
at the point of
And the
discontinuity
very
make any
maximum
difference for the heat
person
flow
who can
problem?
graph it.
For that matter, what does
that's
it really
photon.
mean to solve a PDE
Bottom.
with a
Guess
discontinuous
what,
initial
Murphy?
condition?
Your time to shine.
Can we be sure that the limit of solutions to
We're
the
gonna
heat
hold this,
equation is
hold
also
this
a
fucking shit
solution?
together.
And can we be sure that all functions actually have a Fourier series like this? If not, when not?
And this is
These are
after
exactly the
we've
kind
done
of
both of
questions
those
which
things. The
real analysis
scientist
is
mull
built to
over it,
answer,
and he
but
becomes
it falls a
the
bit
Murphy.
deeper in the weeds than I'd like to go here,
Jason
so
Mule
I'll
ends
relegate
up
that
there
all to
with a
links
guy
in the
named
video's
Al.
description. The upshot is that when you take the heat equation solutions associated with these cosine waves, and you add them all up, all infinitely many of them, you do
Doom
get
Slayer,
an
yep,
exact
I'll take it.
solution
Doom.
describing how the step function will evolve over time. And if you had done this in 1822, you would have become immortal for doing so. The key challenge in all of this, of course, is to find these coefficients. So far, we've been thinking about functions with real number outputs. But for the computations, I'd like to show you something more general than what Fourier originally did, applying to functions whose output can be any complex number in the 2D plane, which is where all these rotating vectors from the opening come back into play. Why the added complexity? Well, aside from being more general, in my view, the computations become cleaner, and it's easier to understand why they actually work. More importantly, it sets a good foundation for the ideas that will come up later on in the series, like the Laplace transform, and the importance of exponential functions.
These are a bit
We'll still think of functions whose input is some real number on a finite interval, say from 0 up to 1 for simplicity.
You got a night shift for
But whereas something like a temperature function will have outputs on the real number line, this broader view will let the outputs wander anywhere in the two-dimensional complex plane. You might think of such a function as a drawing, with a pencil tip tracing out different points in the complex plane as the input ranges from 0 to 1. And instead of sine waves being the fundamental building block, as you saw at the start, we'll focus on breaking these functions down as a sum of little vectors, all rotating at some constant integer frequency.
I'm probably as good at breaking people like this as you would be.
Functions with real number outputs are essentially really boring drawings, a one-dimensional pencil sketch. You might not be used to thinking of them like this, since usually we visualize such a function with a graph, but right now the path being drawn is only in the output space.
0.
If you do one of these decompositions into rotating vectors for a boring one-dimensional drawing, what will happen is that the vectors with frequency 1 and -1 will have the same length, and they'll be horizontal reflections of each other. When you just look at the sum of these two as they rotate, that sum stays fixed on the real number line, and it oscillates like a sine wave. If you haven't seen it before, this might be a really weird way to think about what a sine wave is, since we're used to looking at its graph rather than the output alone wandering on the real number line. But in the broader context of functions with complex number outputs, this oscillation on the horizontal line is what a sine wave looks like.
They're really close. Really
Similarly,
close.
the pair of rotating vectors with frequencies 2 and -2 will add another sine wave component, and so on. With the sine waves we were looking for earlier, now corresponding to pairs of vectors rotating in opposite directions.
And I could do it from my chair.
So the context that Fourier originally studied, breaking down real value functions into sine waves,
I don't care.
is
I
a
just want to
special
be able to
case of
simulate
the more
pick it
general
up. This
idea
thing's
of
little
2D
gloves, power
drawings
gloves,
and
put it
rotating
on
vectors.
thing. It's not heavy. That's okay. You're not supposed to know that right now, little guy. It'll be fine.
And at this point, maybe you don't trust